So this starts our section on designing masonry, and you probably wonder how we're going to fit everything in at the rest of the semester. But the fact is, a lot of what we covered at the beginning of wood, including kind of the look at using it for lateral loads, as well as primarily the wall pieces that we talked about, and then more importantly, the allowable stress design, or ASD. Ooh, that's thick. ASD that we used in designing wood is also what we're going to use for designing masonry. The other item is that the fundamentals of how it behaves is pretty much the same as reinforced concrete. So I'll talk about the differences as we get there, but you've actually learned a lot of the theoretical piece and basic design principles for masonry from all the stuff you've already had in your concrete class, as well as some of the items that we covered in allowable stress design for wood. Masonry is, for most design purposes, the place you'll see it the most is in wall structures. So that's where we'll focus a lot of our attention, but we'll start out with some beam examples as well. So to get started, this first module is going to be the background, like we often do. So let's start out with the history. I'm going to cover a lot of this stuff fairly quickly. You have a full note packet, and you can use that as a reference material. And we'll have 3 homework assignments in this section, and that's it, because we're going to focus on the types of masonry units that you're going to encounter in practice. Okay, so masonry's been a long time. If we look at the very beginning as stone, okay, that's considered masonry. Clay, and then now our concrete masonry units or the blocks, as well as bricks. So these are some of the earliest types of structural construction materials. Through the mid-1800s, they were the primary building materials. As we got into the late 1800s, we didn't have the dominance with masonry because we started to have other products being developed. And if you've taken the history of structures class, I know that I say that stuff a lot, but if you've taken that class, we march down the timeline, and if you recall, we start with stone, and then we move into basically masonry, cast iron, steel, and reinforced concrete. So the 20th century, in other words, the 1900s, is when we first started seeing steel reinforced masonry. So masonry can be reinforced similar to what concrete is. High strength mortars, higher strength masonry units, and then we could see a lot of different sizes, colors, textures, and also have coatings on the material. So we've continued to develop from, the days of Stonehenge up until present. Stone is basically natural stone and packed oftentimes to even it out between with soil or earth. Later on, they started shaping those units so that they could fit more closely, so shaped into more of a block-like unit. Mainly sandstone and limestone are their sedimentary rocks. And now most true stonework is actually more of a non-structural application. It's a veneer on the outside, and we use our CMU blocks or something else precast behind that as the structural component. So Machu Picchu, the pyramids here. Early uses were pyramids and walls. For obvious reasons, I can stack stone in a pyramid, and knowing that stone, like concrete as a material, is good in compression and not in tension, particularly when we're looking at stacking blocks. Likewise in walls, although the better the material between the stones became, the more I could use this as a true kind of retaining wall, as you see in this picture here. We also saw columns and towers. Of course, the Leaning Tower of Pisa there, but that's a foundation issue, really. You can see the stonework is in pretty good shape. Why columns and towers? That, again, compression controlled. Here's Inger Tower. This is another stone. There's actually a lot of stonework around Duluth. Because Duluth had so much growth at the turn of the 18 to 1900, early 1900s. We have a lot of historic structures around here. We have a lot of houses that actually have stone basements, stone walls, brick as well throughout, not just brick facing. So Inger Tower is a good example. They can be used as beams or lintels. So in this picture, we're looking at Stonehenge, and these are kind of the very first look at beams, right? So these beams are made of stone, but they can only span so far because compression is the dominant or is the thing that the stone can handle the best. And so we got to really minimize tension, so we can't get a very long span. Here's some early. Also, you can kind of see the beams or lintels, as we call them, over openings in this case. And then we move into arches. Just like in the history of structures class, we start looking at arches because we started looking at how we could use stones for bridges. The first iteration you would see is something that looks more like two corbels coming together. So if I have a column and a slab, right, I can have a corbel that helps keep the punching less of an issue. If I continue to look at that and continue to stack more and more corbels, right, eventually I put two of those next to each other and I've got an arch. Okay, so that's what you're seeing in these pictures here, essentially two stacked corbels on top of short columns together that form early arches. Then we get a little better at this, and around 1400 BC, we start to see some actual arches. In other words, I'm really using the arch form, which is in compression. So throughout here, this stays together even without mortar or anything because it is in pure compression. So as the loads come down, the arch wants to push out in this direction, but it's being held by the walls here. And so the arch ends up being all in compression, and it's resisted and held into place at these ends. Here's another arch example up top and some down below here. Yeah, the wedge-shaped stones helped form this semicircle in this case. Now, if we go in the 3D direction, we start talking about vaults and domes, which are pretty complex structures actually, but can be done because we're relying on that shell arch and it being in compression. Okay, so pre-Sumerian civilization, Mesopotamia, as ancient as 6000 BC, more of these beehive-shaped domes. So a fairly complex shell structure that is complex to analyze, but as far as just using the natural behavior of knowing that I can put this into complete compression, I'm able to do this dome structure even well before well into the BC. All right, so today, which is what we're most interested in, we essentially have CMUs, or concrete masonry units, and those are used for foundation walls, support walls, and low-rise buildings. They are backup walls for facing, like brick facade and things like that. We also have brick and stone that we still use. A lot of that's used as facade. Other facing materials that can be veneers and decorative walls. So these CMUs are the primary item that you're going to be interested in designing because this will be, particularly around here where we're in a non-seismic region, these can not only be foundations, but they may be the walls that you have as shear walls around your elevator core, where you really only need the lateral resistance for wind rather than a high force like earthquake. So we'll talk about how to do the different types of walls. There are certainly many buildings around the country that are unreinforced masonry brick. Okay, this one is a solid brick wall or a full brick wall with no other masonry, 6 foot thick at the base, 1 foot thick at top, so it's kind of into a pyramid type shape as it moves up the height of the building. So this is a pretty tall structure to be unreinforced masonry. This is in Chicago. I went to undergrad and got my master's degree in St. Louis. That is in a high earthquake zone because of the New Madrid fault. And at the time, nearly every building in that town very huge part of the infrastructure there was built around the time where unreinforced masonry was widely used. We weren't a seismic zone, and so everything was unreinforced masonry. Same with Memphis. Since that time, they have retrofitted a lot of those buildings, and so today, if you're in any seismic risk area, you definitely would not have an unreinforced masonry building. It's going to crumble like stone. We do put reinforcement inside the masonry units, and there's some additional things you can do in a seismic region, but even in a wind region, we would put reinforcement in there, and we'll talk about that. All right, I'm going to go ahead and keep going here and do clay masonry units. So bricks or clay, these have been used for a long, long time, over 10,000 years. They had started with sun-dried bricks or adobe. They then discovered by around 3000 BC that you could bake or fire the brick, which increased its strength and durability. And here's something that's very fire resistant because it's actually made by firing. In the mid-1800s, there was a kiln that allowed the bricks to be fired in a continuous process called the Hoffman kiln. So clay bricks generally are on a 4x4-inch module. So you can see these guys. So 4-inch in this direction, and then 2 sets of 4 in this direction. And then these are the nominal, and these are the specified dimensions. So just like with wood, this is a 4x8 brick, but it's actually a 3 5/8 inch by 7 5/8 inch. A little different than wood, but same thing. You've got actual dimensions versus the nominal dimensions. You also, part of this is the mortar joint. So if I'm looking at a 4x8, there you can include the basic width of the mortar joint in there. It gets you, if I count up the bricks on a wall, that allows me to count up in 8-inch increments. So clay bricks are essentially solid. So more than 3/4 of the cross-sectional area is there. So with just the little hole cutouts, those are typical of veneer bricks. There are larger sized bricks, and those may have larger cutouts. And in that case, you can't just use the gross area. You need to use the net area, so the actual area. There's 3 grades of brick. So all this intro stuff is, there's a lot that's unique to masonry, and so I'm going to just give you these overviews. You're not going to have homework on this, but you'll have a multiple choice quiz. But this is to familiarize yourself with the material. If you've been able to work in the field and see some of this in place, that's a great advantage. If you haven't, keep your eyes open for projects that are under construction. It's actually almost a lost art in some cases to be a bricklayer, and watch how they do that. And I'm going to go into some of the details around that you may not have known. All right, so there's 3 grades of brick, which you may also not have known. We have those that are for severe climate, moderate, or ones that are basically negligible. In other words, they're interior. So 2 grades for hollow brick, and then the negligible, like I said, is really not an exposed brick. So as with everything in Minnesota, we're in other than seismic, we're in one of the toughest regions because of the weather. And so in our region up here, and all of Minnesota, essentially, we need to have the severe weather brick. It's due to freeze-thaw cycles, although I would say that depending on the year, there's less here than, say, in Missouri, because not permafrost, but we stay below freezing. But we're considered in the zone of high weathering, and so we would need to use the SW bricks for any exterior application. So how do we make bricks? The oldest process is to basically press the mud or the moist clay into molds. There's a dry version of that, dried clay, that are pressed into steel molds, and then there's the extrusion process. So it's kind of a stiff mud, like if you look at an extruded hollow core piece of concrete, where you have very little slump. They extrude it through a rectangular die and then chop the pieces up. this is most common. So this extrusion process is the most common today. Firing, you can have a kiln where you basically do the process like you would a ceramic piece, where you fire it, cool it, and go through the whole cycle for a load of bricks, or the tunnel where they're passed through continuously, and that's obviously a faster process and more of an assembly line type process. Your color of bricks varies, so some of that's the clay that's in the brick, the chemistry and temperature of the kiln fire, and then you can be intentional about the composition so that you can get kind of the blonde brick or the red brick, but there's still variations even within that. There's no real standard size for brick. I showed you kind of the typical brick, but they're not completely uniform, and there's many other sizes besides that kind of 4x8 brick. A normal course is 3 bricks. So if I put 3 bricks, that I get 8 inches with that course. So they're looking more in this direction. Oops, sorry. In this direction, which lines up with the 8-inch CMU blocks that we'll see, or a sideways brick, right? So you see here's my 8-inch brick, and if I line up these sideways, I also have about 8 inches. There are larger size, there are custom shapes, there are custom colors. I mean, you look over here and you've got not a standard brick by any means. Okay? So you can do anything you can mold, basically, you can do. Similar to concrete. So I've got a cool facade look to this brick. It's also a longer brick. You've got some custom pieces here, these rounded pieces, etc. Okay. Of course, those all cost more. There's a really unique brick structure where they've put an inlay as part of the brick itself. Took some time to do that one. When you're choosing brick, you're going to look at the color, size, grade, type, your exposure, and then what process is used. You can see some of these are a lot slick and shinier than other ones of these, and I'll show you how that happens. And here's that. So you've probably seen all of these. Here's an older one that's from a wood mold down here. You see a lot of these extruded smooth bricks. Okay, so this is the side of the brick, right? It's going in like this, and so it was cut across that face, and this is the smooth extrusion side. These guys were extruded, but then cut on this face with wire. Okay, so it just depends on what you're doing, and you can kind of see how they're extruded. Here's a smooth one. These are the ones you commonly see in the real thin veneer brick. So I drew it going into the page, but it might only be a very thin veneer backed by CMU or masonry units. And then, of course, you've also probably seen these rough brick, the raked brick, similar to what we see in a lot of precast concrete structures. So the strength of the brick depends on both the brick itself and the mortar between the brick, right? So you get 2 components, and the mortar is a composite, just like concrete. And so both of these have to do with what your actual strength of this brick wall would be. So let's talk a little bit about brick terminology, just so you've seen it. We've got the head joint, the bed joint, that's along the length, and a course is a horizontal layer of brick, so a course of brick. A header bonds the withe. So the withe is 1 vertical layer, 1 unit thick. So this is a withe. The header, it's pointing, but not so great. These bricks that are sitting going into the page, those kind of pull the wall together so that I don't just have a skinny stack of bricks, right? So if this is 2 bricks wide, of course, on both sides, that would be the one that branches, similar to kind of this picture. Okay, now these particularly are laid they're on their face, okay, with the end visible, and that's called a row lock. A stretcher is when you put it long dimension horizontal with the face parallel to the wall. A solder is laid on its end with the face parallel to the wall. Okay. Brick bonds, so structural bonds. So we got our mortar and our orientation here that forms the bonding of this wall. And with veneer type walls, here's a couple options. This one is stacked, and you just don't see that as much anymore. I think for, if it's a veneer, fine, but it's really not the structurally robust shape that you have when you do this kind of alternated pattern that we're used to seeing. But you will see these stacked sometimes. Here's one that's utilizing a bunch of the different things I just talked about in kind of it both ties the walls together. It's also an interesting architectural feature. And I'm going to pause there, end with the bricks, and then I'll start up the next one on CMU.